Now I will leave. Anton, Caceres.
Caceres, that's right.
Thanks.
Hello everyone, thanks for coming. So, I'm going to talk to you today about the asynchronous web and how did it change with Python 3 coming. So first of all, of course, I'd like to introduce myself. I am a full stack developer, but I'm mostly a backend guy and I'm focused solidly on Python for the last 5 years or so. I work at Scooby in Munich, and that's a company that does the ebook flat rate. So basically it's like Spotify, but for books. We have a lot of books now, unfortunately not in Italian, but that is coming. We do apps for Android, for iOS, and people like those apps. And the most important thing is that we use Tornado in production. So, I mean, I know what I'm talking about. You can trust me, this works. So our everyday challenges include our distributed systems that we need to maintain, that we need to keep it efficient. We need to keep it low latency because the users don't want to wait when they read a book. Also, of course, apart from that, we are migrating to Python 3. And saying that, I can tell that some modules already run on Python 3. So again, this is something that I would like to share with you today because we love to share. Let's see the talk overview. So first of all, I'm going to discuss why actually we need this asynchronous stuff. Like this buzzword is all around now, but do we really need it and why and when? Second, I'll come to what are we actually getting with Python 3. And that is first of all yield from, so the generator delegation syntax. Then Asyncio module. And then I'll cover the Tornado part as a library that can let you use all of those stuff already now. And if we will have time, hopefully we will, I will show you a little demo how does Tornado actually perform comparing to other web frameworks. Okay, so why we need the asynchronous web server at all? And we can start with a quick recap here. So how do web servers actually work and how did they work? How did they used to work? Let's start with a threading web server. So this is like the most straightforward idea. A new request comes, let's just have a thread for that. Exclusively, let's do everything related to this request within this thread. It's pretty easy, it's pretty straightforward, and it worked for a pretty long time. Until we get out of memory or out of any other resource of our operating system when we cannot scale anymore. And meaning that we cannot scale also means that the threads that are already opened can freeze. So not only new users will get the denial of service, but also the users which are already connected will get some nasty errors and bugs and so on. So the idea was, okay, if that's a problem, why don't we limit amount of threads in a pool? So say we have a n amount of threads or processes, we fix it within a pool, and so if we have more requests come in than the size of our pool, they should just wait. That's a nice idea, and it worked pretty well, because with that, we at least are not causing trouble for the users that are already connected. So they keep served, and the new users are just waiting for the free spot in the pool, and as soon as the spot arrives, they get it. So this also worked pretty fine, but then we invented WebSockets, we invented long polling, we invented lots of things that require to keep the connection alive, and so that meaning to occupy the slot in the pool for a really long time without actually doing nothing. So the threads in the pool with the long polling approach are just idling, they are blocking, they are waiting for the I/O, which doesn't come. I mean, most of the time, threads do nothing in the thread pool, even without long polling. We always wait for a database, we wait for our, I don't know, some third-party API or whatever. It's a very rare case when the web server really waits for the Python code executing on it, like some crazy math, I don't know. I don't even have example for that. So we usually rely on something else. And relying on something else, meaning that the thread waits for the I/O in 90% of cases. So is there a smarter way to use our operating system resources? And this is how we came to the asynchronous web server. So I guess everyone is familiar with it in one way or another. Everyone probably heard of some buzzy articles on the internet how Node.js can handle, like, I don't know, a million of connection on EC2 micro instance on Amazon. Though that's all true if the bottleneck is I/O. Because asynchronous web servers, they have just one thread usually. And this one thread handles everything. So it delegates the task of jungling with sockets and with connections to its core I/O loop. And then the operating system is doing the real I/O, like asking for a socket, opening connections. And when data arrives back on that socket, it knows who was asking for it. So basically, the picture is reversed in comparing to the pool of threads. So we have just one thread. And around this one thread, we have connections going and waiting and doing the I/O. I'll, of course, explain it more detailed. This is just an overview and motivation, like when and why do we need this at all. So async is not a novelty. Like it was not introduced in Tornado. It was not invented in Python. It was there like for ages. Tornado is actually 6 years old, and Twisted is 12. And the world is not just Python, right? So there are many, really many of the frameworks and web servers that can do the asynchronous I/O. But why do we use blocking servers then? Like the idea is not fresh again, but why don't we use it? Well, obviously, sequential code is easier, it's more maintainable, we love it, we understand how it works. That's why we use it. And as a proof of that, you can think of Django, Ruby on Rails. So simplicity matters. When you can do something efficiently, that's cool and people will use that, right? So when we develop the code, when a company develops the code, it shouldn't be only efficient for the server. It should also be efficient for the developer that is doing it, right? Because developers also cost, and it should be used in a nice way. So now the question is, what if we could write the asynchronous code in a sequential style? Of course, it's not possible to say completely in sequential style, but at least similar, like so that we minimize the effort to switch from the asynchronous code to asynchronous code. That's a nice idea, and Python 3 gives us a tool to achieve that. Those tools are basically the yield from syntax and the asyncio module, which I will focus on in a minute. So first, let's discuss the yield from. This is a generator delegation syntax. It was introduced in Python 3 recently. I haven't seen a wide use of it yet, which is sad because it's pretty cool and usable. So it aims to replace callbacks when we write the asynchronous code. What's actually bad about callbacks? Like, we probably all did some JavaScript, so we have some experience with writing callback-based code. It's not like it's bad, but it's not very nice. And I don't know, do we have some JavaScript coders here? Okay, very nice. So you all know how painful is it to maintain a big, really big project that is callback-based, especially when you define like inline functions one under another. For those who don't do JavaScript, I can show. This is how it can end up. It's not that I wrote that code, it's Mongo.js. I was just looking over the GitHub, like how can it be? So of course this is code just for testing, so the aim was not to make it beautiful, but still, like if the simplest way to do something is like this, you have a problem. So sequential code looks obviously much nicer, and it's easier to maintain, it's easier to debug, it's easier to write and extend. So the yield from syntax that was introduced in Python 3.3 is going to change that. Let's focus more detailed on this slide. So this is a example of the sequential get request handler. This is just some function, as you see, the get request handler that does some huge database query. Can I point here? Yeah, I can. So this is a huge database query that is done. Then the result is written to result variable, and we use self.write to write this result somewhere to the client. So where will the blocking appear in this code? obviously, huge DB query will wait. So how would JavaScript guys solve this? They would define a function, another one, that would handle the result when it is available. So we would do something like this. We would write the huge DB query and pass it a callback in so that when the result is available, this onResult function would get called, and then, yeah, we would not block then, but we will need to have some kind of weird syntax in there. And what can we do with a subgenerator-based handler? So this yield from that I was talking to you about over here is replacing callback in this example. Actually, who used yield from already? Okay, at least. Who used generators in Python? Wonderful. Okay, so then it's easy. So just a quick reminder that the generator work both ways. It is often a cause of the confusion. So generators can not just yield some variable back to the caller, but they can also push something inside of the function back. And this is exactly what happens here. So the huge database query is yielded to the IO loop. IO loop makes actually the query using the operating system resources. So I will focus on this more detailed on the next slide. So imagine that that's a magic that IO loop does for you. The idea of the syntax here is that the huge database query will not block. It will pause the code at this point where we see the yield from expression. Meanwhile, the thread will do some other task, something else, and as soon as the result of huge database query is available, it will be sent back to this point and saved into result variable. So you can think of yield from keywords as of sign to pause a function. So you put it on hold until the result will be available there. And then we continue normally, we just do self.write. So now to explain how does that work, we are coming to the Asyncio module. So again, this is a new module, but the idea is pretty old. So Tornado had their own IO loop implementation, then there was also the Asynchronous module from Python 2 already. But the Asyncio from Python 3.4 is like a standard way to do things. So it's really important to use that and not third-party libraries, because that is a standard that is going to change how frameworks also interact with each other. If we use a standard core, it's obviously better in the long run. So first, let me speak about the event loop. It's a core of the Asyncio generally. Event loop is something that will manage your whole application I/O for you. It runs in one thread. You can have more than one I/O loop, of course, but you usually need just one. So I/O loop will save information about callers that need some data. So when you do, let's say, a huge database query and you yield a feature back to Asyncio, it will remember, so at this point, this function wants the result of this whatever, this generator. So the task of the event loop is to keep this mapping. So who is waiting for what? And on another side, keep track of what does the operating system tell us via its interfaces. Like, for example, operating system will tell you, hey, you asked for data on this socket and now it's ready. So these are operating system modules, that's KQ, ePOL, and others that are integrating with the IO loop here. So operating system will tell, okay, data is ready on this socket. Asyncio event loop will see, oh, okay, on this socket, then that's most likely the huge database query result. Then it will look up who was asking for it. It will find our get request handler, and it will push the data back there. That's how it works. And as soon as one get request handler, for instance, will ask for the huge database query, it knows that, okay, now it takes some time for operating system to fetch this thing, so I can switch to another task, and it will keep this switching. So that's basically, in a nutshell, what the event loop does. I put some sample code here, so that's the easiest way how can we start the I/O loop. We are not sending or receiving any data over the socket here. We just have a hello PyCon function that will be scheduled in the I/O loop and executed immediately. So here we define a function here. Then we get the I/O loop instance. It's usually a singleton. Then we call the call soon function on the I/O loop, which means just call on your next iteration, so meaning as soon as possible, call this. And the last thing, we need to start the I/O loop, so it takes control of this Python process and runs the stuff. So that's the simplest case. To make it more interesting and more tricky and more usable, we are coming to the futures concept. So I guess JavaScript guys already know the futures from deferred in jQuery or promise in Angular. So futures also existed in Python, of course. Long ago, it was concurrent futures model, and it's pretty much the same as Asyncio future. Who used concurrent futures? Okay, so makes sense to focus on this again. So future is basically a pretty dumb thing. It's just a placeholder, a wrapper that will indicate you when something is ready and will keep a reference to the result of this something. So again, future is not doing anything. It's just some dummy object that has a state, is it done or it's not done, and it has a reference to the result, and it can keep the information about status of it's in process or is it cancelled and so on. So it's just some dummy object that is very easy to exchange between pieces of our code. Meanwhile, on the background, some other job is executed to really do stuff to fetch the result. So you usually never create futures by hand. So it's almost always that some library will do that for you. For instance, if you need to fetch some URL, that would be your HTTP library. If you need to fetch a database result, then that will be a database driver that will create it for you. Yeah, so you pretty much always use some library to create a future, so you don't need to know how is it constructed. What you need to know, though, is its interface. So future has a result, but usually never call the result directly again, because if you use the yield from syntax, then the result will be unpacked for you. So basically, future is this placeholder object that the I/O loop is waiting for you to yield to it. And then it's a task of I/O loop to figure out when the future is ready and to give you back the result. So if you use Tornado, then you don't even need to know the interface of future. Let me show you two examples here. So the first is the simplest way to run a future. The I/O loop just has a method run until complete here. We pass it a future, and then when the future will be ready, we can call the result method and get the result. Then example 2 with yield from. We have a coroutine. We use the HTTP library to fetch Google.com. This will not return us the real body of the page. Instead, it will return us a future, because this is a asynchronous HTTP library in this example. So we need to yield this future back to the I/O loop. It knows what to do with it, and as soon as the future will be ready, I/O loop will send it us back, and we'll save it in the result variable. That's it. And of course, we need to start the I/O loop. Next, Tornado. So I tried to cover briefly how does Asyncio work, what is the syntax about, but since that's pretty fresh stuff, it's a pretty new thing in Python 3, we need some frameworks that can already do that. So I have only Tornado in my mind. If anyone knows anything else in Python that can run this already, tell me. I'll extend my presentation next time. But for now, we have just this option. So Tornado has its own event loop, as I told. So it existed long ago. It was also usable in Python 2, but in Python 3 it's of course much better. So we can use the Tornado I/O loop if we are on Python 2, or we can use the Asyncio event loop if we are on Python 3. The choice is up to you, of course. some of us have a critical requirement to run Python 2.7, for instance, on some of their servers, so that's possible. By this, I want to say the advantage of having your code in Tornado that you can easily switch the IO loop. It's basically one line. Then the futures. Futures also available in Tornado as an own implementation, as well as you can use futures of the Asyncio module. So let's say that I developed my application 4 years ago with Tornado. What I would need to do now to switch to Asyncio is first switch the IO loop, second switch futures. That's pretty easy. It's this bridge function that can do that for me. Now let's have a minimal example of how does it really work. So this is a full example now in Tornado, a full class that is handling GET requests for us. Let's go just line by line here. So first, we need to inherit from the request handler of Tornado. Then, this is the interesting point, we mark our GET function as a coroutine. Who knows what a coroutine is? Okay, so just, well, in this simple case, the only reason to have this decorator is to tell IO loop and Tornado that this GET functions that I'm decorating will yield us futures. So basically, it's just an indicator, a tick that, hey, this will be asynchronous code here, because Tornado can also run in synchronous mode. So we define our GET function, then we have our async HTTP client here. This is a library of Tornado that will fetch URLs for us, basically, but return us futures instead of the real results. So not block, instead return the future. Then we run the fetch method of some really slow API URL, and we yield it immediately. So we yield in a future back. Tornado sees, aha, this is a coroutine and it's yielding us something. We need to process it. Yeah, please. How do I handle what? Excuse me?
Say you have a 400 instead of a 200 from that server. In Angular, you would have a success error callback. So.
Yeah, that's a very good question. So generally, how do exception pass here in this case? So as it was mentioned now, that the advantage of the callback style is that you can have multiple callbacks per one function. So like we used to do in JavaScript a lot, we can have on success, we can have on error, we can have on bytes if we like anything. So here obviously yield from means just one callback, right? So the callback is what is below. That's a callback basically. So to handle like multiple results that we could get here, the only way that we can rely is just to use standard Python exception handling. So in this example, if fetch will return 404, it will raise an exception. And we can wrap this yield from blocks with a normal try except. That works pretty fine. We can also, however, in some libraries, like in this example, HTTP client, if we really want to use callbacks, we can have it too. So after this, you can specify comma on error callback and specify Python function. It's considered a bad style because you're like mixing two concepts, but in some cases you really need it, and then you can have it. Was that the answer? Okay, very nice. Good. So yeah, I think we're through with this example. Now, just to be fully honest with you, of course, I had to show you everything that you need to have this example really running, including import statements and the code to start the IO loop. Because we all like Flask, because it's so little and it's so simple and it's so easy to get started. So Tornado is not much bigger. That is all code in one file that you need to get this request handler to work. Yes?
In case we have a big result set, a big amount of data, we want to write back to the client.
Mm-hmm.
Can we do asynchronous data
Can we do
writing asynchronous operation on the data brought back to the client.
So not just reading something asynchronously,
Exactly.
but also
Yeah.
returning it, of course. And Python generators play a very cool role here. So basically, you have here a self-write that will write data, and you can also put a chunk of data there. That works pretty well. You can have an iterator loop or a generator loop here that will do that for you. And you need only to call finish at the end so that it will close the connection. So that's basically the only requirement, is to call a finish at the end. But you can call write from any point of your get request handler. You can also put it to another function if you pass the reference to it. You can put it in the sub-generator if you like. So it actually works pretty well. And a good example for you would be WebSockets. So it's pretty easy to implement it with Tornado. It's smart enough to not waste resources on that. You can fully rely on generators. One more thing that maybe I didn't point good enough is that here, the yield from thing can not just handle futures after it. It can also handle other coroutines that yield futures, meaning that you can stack one function under another function like that. So you can have here not something that will return you future, but just another generator. So, okay. Yeah, all right. Good. So here at this point, yield from, over here, you can specify any other generator, any other coroutine that will do the same thing as this one. Meaning that as we are so used to writing our normal code, we can call a function from another function. In the same way, we can call a coroutine from another coroutine. And this yield from magic will handle the case when the future will be popped up all the way back to the IO loop from any library that's somewhere, we don't even know where, most likely. That's what I wanted to say. So, and then it's actually pretty handy that the exception handling is also happening in the standard Python way. So you wrap with normal try except blocks your calls, and exception will also pop up just the same way as we have it in normal functions. Good. So before I, how much time I have? 7 minutes. Okay. Yeah. Okay. So then I would just like to show you a little example, since Python is not the only thing that can do that. I am sometimes collecting the same thing, but implemented in other frameworks, in other languages. So it just may be something that will be interesting for you. So first I will really quickly explain you the use case for this. Okay, so imagine we have a client, that is us right now. We have a web server. This is meant to be Tornado, what I was telling you about. And we have some APIs. Imagine it's, I don't know, a search. We want to search simultaneously on multiple search providers. This is Google, Bing, DuckDuckGo, whatever. And our client asks for some query. We are basically the proxy here. So we are asking 3 different APIs. What we do here is just normal GET request. So it's a perfect use case for this kind of task, to do these 3 requests asynchronously, meaning in parallel instead of blocking and waiting. And now I will just show you the code that is doing this in Tornado. Here it is. This is the synchronous code. So there is no yield, there is no coroutine. How quickly can I make it asynchronous? It's pretty fast. First, a coroutine. Not there. Yeah. Okay, first, the coroutine. Second, I need a library that supports yield and that supports returning futures instead of blocking. So this will work. Third, I need to yield it. I can also use yield from, but in this case, yield is enough. This also works on Python too. So that's basically it. That's everything that I needed to convert synchronous handler to the asynchronous handler. Now all of these 3 fetch requests will go asynchronously, meaning in parallel. We save time. Node.js. This is already a asynchronous implementation. So there are libraries that can make it smaller and more beautiful, but I tried to, I asked, it's not my code, of course, so I asked a guy to use minimum dependencies. So this is how it looks like. I think that we have still a couple of minutes, so we can quickly maybe say it. So basically, it's a pure callback-based solution, and we are defining callbacks just here in line. As you see, we receive on each chunk of response, we push it back to some array, and then when the end happens here, we are concatenating all of these body chunks to some buffer, and then, yeah, we are parsing the JSON and sending it back to the client. So basically, in a nutshell, how it works. Then, Pinnacle. It's a nice tool from Scala. Scala is a really cool thing. So I'm not using it because it's too hard for me. But I know that it's cool because it's fast. So this is a Scala example. It's also not so small, but it looks quite friendly to me. Okay, 5 minutes. Let's not stop here on this code. Let's better see how do they perform. So here in this IPython notebook, by the way, who uses IPython notebook? Nice. Did you know that it's on Tornado? Cool thing. Yeah, I will not run it. I have here. I have a backend that already runs it. So just to show you how it works, this is a hello world string that it returns you, and this is a timeit function saying that we need 22 milliseconds per loop. Just to have some comparison, here I have the blocking server. It will do the same task, but within 55 milliseconds. So it's almost 3 times slower, obviously, because it's blocking and it's waiting. Let's run node example. $19, which is faster actually than Tornado. Well done, Node.js. And finally, Scala Pinnacle. 18, even faster. Okay. What is interesting here is that we have this example of 3 APIs calls at the background, yes? What if we have 10, 100, maybe more? So I will be answering your questions now, and meanwhile, to save time, I wrote here a wonderful function that will increase a number of these APIs that are called on the background from 1 to, I think, 20. And we will see how does this scale for these frameworks. So it takes quite some time to run this thing. Meanwhile, let's start with questions.
You said you're using Tornado in production, so I'd like to ask if you could give an idea of how many connections, how many traffic basically you handle on a certain size of a server, assuming like AWS as a standard.
Yeah, so I never tried to run Tornado in production on small instances, honestly. So we run it on the large instance, but we have just two large instances, load balancer, standard thing basically. Also, we do not have WebSockets, so I do not have really this big amount of the connections that are kept alive. But yeah, just to give you the idea, I don't know. I can give you the idea that before that I used Django. And for Django, I needed, within the same setup, I would need about 4 times more machines than now. It depends a lot on the nature of your requests, of course. Like if you are waiting for the database, it doesn't matter. It's Tornado or it's Django. But since in our case we are extensively caching everything, and we do not do direct data collection, we have some magic, you will not see a really good benefit of Tornado. To see the most that you can push out of it, you need to use WebSockets or any other thing that really requires to have a lot of the connections in parallel. While the normal websites would also do quite well with putting Nginx in front of whatever frameworks that you use, even WordPress, anything. So.
How do you use yeah, G-Unicorn on a large instance, you have 8 CPUs, you have 8 concurrent threads, basically. Here you will have only 1, I guess.
Yes.
Right?
That's right.
So even the machine can be scaled down, probably, the size.
Yeah, so the thing is, as I told, this is a very interesting fact that we almost never wait for Python code. We always wait for something else. So you really don't notice that you are not using more threads because you're always waiting for a database, a caching system, or another API. You never hit this limit, in my experience. But on the large machines, as you told correctly, you have more processors. Obviously, you are wasting the power because you're using just one. So solution is very simple. Run 4 tornadoes if you have 4 cores.
We have a similar case. We have 2 tornadoes using the CPython. You have the GIL lock on threads. So we have 2 tornadoes. One is the web and WebSocket 1 serving. The other one is doing a heavy cryptography, which is blocking as well as I/O from the web server point of view, because it's very heavy computationally. And we managed to use an event-based like Tornado because we made the cryptography calculation on one Tornado, which is RPC called by the other one, using yield from. So this is another case where you can use more CPUs using more Tornadoes. You are solving a computational problem which is different from the I/O problem, but is solved by Tornado. And also, basically, if you add more machine, you can have more processor, and so spawn more threads. Even though you can spawn a thread from Tornado loop, and then have a future, or the thread, I don't remember the name, which tells you the thread is done, here is the result. So basically you can spread more, you can spawn threads on spawn processes and get the result back, even using one only event loop.
Yeah.
Currently.
Yeah, so thanks for your notes. That's right. I think that we could make a whole another topic on scaling Tornado. That's also quite challenging thing. Today was more like introducing it to you, so you have time until the next PyCon here in Italy to try it, and then maybe you need to scale it, and I show you how to scale it. Last thing, we have results here. So, Tornado is blue line. As you see, it was slowest at the beginning, but as soon as we have more than 5 background requests, it's better than Node.js. But it loses to Scala, which is normal because Scala is super powerful. That's a result. If you really have a problem with this 15 milliseconds, I'm sorry for you, but I think it's good enough in all 3 cases. So just write asynchronous code, have fun, and yeah, enjoy Python 3, of course.
Thanks.